Hi, Cole.
Hello.
How are you doing?
I'm doing okay. How about you?
Good. Are you back in school?
I'm back in school tomorrow.
Tomorrow. Okay. Well, we got a couple things I would like to do. Would like to continue on the same source that we've been working on. And then I just want to go over with you one problem where you would have to prove something using these properties of equality. And in fact, let's do that first, just so we make sure we get it covered.
Okay.
Now, I don't think they're going to start you off with proofs in geometry, but they're going to come pretty quickly. What they may do is do a week or two of reviewing algebra and stuff like that, but I suspect you'll be in good shape for that. Your algebra skills are pretty good.
Mm-hmm.
So I don't think you'll have any problems with that. Let's talk about what a proof is, first of all. If I needed to prove or solve, rather, if I were to solve that equation, you and I take it for matter of fact that we can subtract anything from both sides of the equation, or we can add anything to both sides of the equation. But it's really not quite that simple. Notice that these are called algebraic properties of equality. So that's what I'm given. And this is kind of the way proofs work, is you have what they give you, and then you have what you can prove. Well, the first thing I can do is 2x minus 18 equals 2. And why can I do that? Well, that's the subtraction property of inequalities. In other words, notice what the subtraction property says. It says if A is equal to B, then I can subtract any number I want from A as long as I do the same thing to B. So if I'm rationalizing that, I have to give the reason. What's difficult about proofs is you have to give the reason for being able to do something. So I would say that is the subtraction property of equalities. All right. The next step, I would add 18 to both sides to get this. And my rationale for that is the addition property. So, in other words, the way two-column proofs work is you work through the solution on the left side and you give the reason on the right. And that's what makes them so difficult. Is that
we did worksheets like this.
What's that?
We did worksheets like this in algebra.
Oh, good. Addition property. Yeah, it's hard because so many of these properties that you take for granted actually have a name for them. And then finally, x equal 10, and that's the division property of equalities. Now, the one that, notice that the addition, subtraction, multiplication, and division, that's pretty easy. All four of those are something you should know. But these four here are new, probably. I doubt that you've seen them before. Notice what the reflexive property is. A equals A, or B equals B, or C equals C. In other words, for any real number, it equals itself. And you wouldn't think that would have to be stated as a property, but it is, and it does. And you will come across problems where one of the steps is you have to cite the reflexive property. Let's look at the next one, the symmetric property. A is equal to B, then B is equal to A. Again, almost seems self-evident. The transitive property. It's a little different. If A is equal to B and B is equal to C, then A is equal to C. In other words, if A were equal to X and X were equal to 3Y, then A would be equal to 3Y. Okay? And that's more of a property. Okay, I can see a lot of things that you would require this transitive property in the right-hand column. And lastly, well, not really lastly, because it's not like all your proofs in geometry or you're going to be able to use one of these 8. That's not the way it is. In other words, when you do a 2-column proof in geometry, you use either an equality property or one of the theorems that you get taught. And you're going to get taught probably 50 different theorems. So the whole thing about proving something is every step of the way you have to cite a reason. And that substitution property says if A is equal to B, then A can be substituted for B in any equation or expression. In other words, if I say A is equal to B and B squared equals 49, then I can say, well, A squared equals 49. In other words, I can substitute A for B in any equation. All right, I think that's as much as I want to say for now about proofs. That's just a quick exposure to you. And I don't know at what point in the school year you're going to get this, probably after a couple of weeks of starting class. They tend to start off geometry with these proofs, which I don't like. I don't think that's the right way to teach geometry, but I am not controlling the school board, so they don't care what I think. All right, let's go back to some of the more basic things in geometry. This one, we've done triangles, we've done circles, we've done quadrilaterals. Now we're doing something called multiple figures test. Okay, in multiple figures, for example, if a rectangle with a diagonal of 5 inches is inscribed in a circle, what is the circumference of the circle? Well, what are they talking about? They're talking about there's the circle, there's the rectangle inscribed in the circle, and they're saying the diagonal of that thing is 5. So what's the circumference of the circle?
5 pi.
Yeah. How about this one here? What is the area of the rectangle? Notice that we have a triangle inscribed in a rectangle. So it's a multiple figures. Also notice that this is an isosceles triangle. And the area of the rectangle is what? What's the formula?
Base times height.
Well, the base is 6. So if we can figure out the height, we'll have our answer almost.
Mm-hmm.
What's this distance from here to here?
3.
Only because it's an isosceles triangle.
Mm-hmm.
Because it's isosceles, you know that this vertical bisects the base. Okay, what's the vertical height? If this is 3 and that's 5, and that's a right triangle. What's your minimum right triangle that's called the perfect Pythagorean triangle?
2, 3, 5.
3, 4, 5.
4, 5.
It's easier than that. It's 3, 4, 5. 3 consecutive numbers. So
Okay.
this has to be 4. Now, I could go through and use the Pythagorean triangle, or the Pythagorean theorem, in which case that height would be the square root of, it always starts out square root of, 5 squared minus 3 squared, which is square root of 25 minus 9, which is square root of 16, which is 4. Okay, so even if we do not remember the 3, 4, 5 triangle, we can always figure out. In other words, you always want to be able to solve right triangles when they give you two sides. That's one of the fundamental skills of geometry, is being able to solve right triangles. So if the height is 4, then the area is 24 of that rectangle. Blow this up just a little. I think that's all you need to see of that. So in the circle above, 3 right angles have vertices at the center of the circle. If the radius of the circle is 8, what is the combined area of the shaded regions? It's a little tricky to be in the basic section.
Mm-hmm.
First of all, let's talk about shaded area, shaded regions. Whenever you're getting asked a question about shaded regions, it is always a subtraction problem.
Mm-hmm.
By that, I mean we are not going to figure out the area of each of these 3 shaded regions and add them up. What we're going to do is we're going to figure out the area of the circle, and then we're going to subtract the area of the white regions. Why? Because those are easy to figure out. Notice that because that's a 90-degree angle, that is 1/4 of the area of the circle, right? Because the whole circle is 360. 90 is 1/4 of it. So whatever the area of the full circle, this region right here is 1/4 of it. So first of all, what's the area of the full circle?
pi r squared.
in this case?
I don't know.
The radius is 8. What is pi r squared equal to?
64 pi.
Okay. So if each of these 3 white areas is 1/4 of this area, that would be 16 pi. 16 pi is 1/4 of 64 pi. So how many of those do we have? 3. So we're going to subtract 3 16 pi's. You see where I get that step?
Mm-hmm.
Okay. Well, 3 times 16 pi is 48 pi. So we have 64 pi minus 48 pi. We have precisely 16 pi in the shaded region. And yet, we don't really have any geometry to allow us to calculate the area of these shaded regions. In other words, we have to do this problem as a subtraction problem. We have the geometry to calculate the area of the white regions inside the circle. We don't know these angles here. So calculating the area of these shaded regions would be tough. We don't even know that they're equal to one another. In other words, we don't know that angle is equal to that. It wouldn't have to be at all. So the only way to do this problem is the area of the full circle minus the 3 areas that we know we can calculate. Because we know that's a 90-degree angle. Okay, they're telling us that a square and a circle have equal areas. Well, what's the area of a circle?
Pi r squared.
What is the area of a square?
Base times height. Or just...
How about x squared? In other words, we can do better than base times height. Base times height is for a rectangle, but a square is a very special kind of rectangle. And x squared is a better thing than base times height because it only has one variable, x. Base times height, that's 2 variables. So if we can make everything one variable, we're better off. And now they say, what is the ratio? And they're saying that the areas are equal. So now I can say pi r squared, the area of the circle, is equal to x squared, the area of the square. And they want to know what x over r is. How do I get x over r?
I don't know.
Well, I want my final answer to be x over r equals something. Well, let's start out by dividing both sides by r squared. So now I get pi equals x squared over r squared. And now if I take the square root of both sides, I'll have x over r on the right side, and I'll have my answer on the left. So x over r equals the square root of pi.
Okay.
You're going to find that most geometry is at least 50% algebra. That's why algebra has to be taught before geometry. Okay, this is a square. This is a square. The area of this is 36. What is the area of this square? So clearly we have to solve this triangle in between, right?
Mm-hmm.
If the area of this square is 36, what is the length from C to E?
6.
So now we have a isosceles triangle that has a length of 6 on the hypotenuse. If we can solve for the sides of that 45-45 right triangle, then we'll be in good shape. Because if we can figure out that side right there, x, then figuring out the area of this square is easy. It's just squaring x. Well, let's examine this triangle. So 45-45, and the way to solve a right triangle when they only give you one side is to refer to the two special triangles. They're only going to do that if it's one of these two special triangles. It's not that one. But it is this one. So, if we're trying to solve for that side, what's the similarity ratio?
Times 3.
Remember, we're not comparing it with the 30-60. We're comparing it with the 45-45. In other words, let's erase this one. That's not in play here. I'm comparing it only with these two triangles are similar, meaning they have the same three angles, which means whatever the similarity ratio is, that's the ratio of every side of this triangle relative to this triangle. Well, how do we get the similarity ratio? We compare the big triangle with the little triangle. That's the similarity ratio. Now we take the similarity ratio and multiply it by that side length, 1, to get this side length, 6 over root 2. So now I've solved my problem. Now notice something. I did not rationalize that. Any know why?
No.
Well, because they want the area of this square. So I'm going to take this number that I got. That's not my final answer. My final answer is that number squared. Well, I don't need it to be rationalized in order to square it. You see, in other words, by the time I get my final answer, it's going to be a rational number. If I square this, it's 6 times 6 and square root of 2 times square root of 2, so I get 36 over 2.
So what is it, 18?
18 is the area. And I didn't need to worry about rationalizing this 6 over square root of 2. Had I needed to worry about it, let's just review. I'm going to multiply that by square root of 2 over square root of 2. And that would become 6 square roots of 2 over 2, or 3 square roots of 2. So I could have done that whole process and worked with that, and then squared this, but notice that's 9 times 2, 18, same answer, but I saved myself a whole bunch of steps by not having to rationalize it, merely because that was not the final answer. In other words, don't rationalize numbers until they're the final answer. You may find you don't need to rationalize them. All right. stop there.
All right.
Number 5 on 180. Hold on. Now, probably from this point forward, if we continue to work, we'll want to work on what you're doing in class, as opposed to this stuff here. I don't know what you guys have in mind, whether you want to just keep this 3:30 half-hour appointment after you start school, or what? Have you talked to your mom about that?
No, I have not, but I can talk to her about it.
Why don't you? And I'll go ahead and leave you on at 3:30 for next Monday. Let me just make sure that my calendar says that. Yeah, it does. And if for some reason you need to cancel or want to cancel or whatever, you can. I'll go ahead and do the accounting. I'm not sure whether you've had 8 sessions this summer, or 9 or 10 or 7 or 6. I don't know. I suspect you're probably a little over 8, because it's been 3 months and you've been pretty much doing 1 a week. So you're probably a little over 8. And just in case your mom wonders, I'll charge you the same rate. In other words, it doesn't have to be a 4-hour increment. I'll charge you $10 per half hour through the end of August. Once I get into September, I go back to my normal pricing, and you guys can just deal with that however you like. But until then, yeah, it's $10 per half hour through the end of August. Okay?
All right.
Well, good luck tomorrow. Hope you enjoy your geometry. I hope you get a good teacher. And I'm happy to help whenever you need me, Cole.
All right. Thank you very much.
All right. Bye-bye.